welcome back. And so after the break, before the break, we just talked about the factorial of n, right? So after the break, let's check out the C code of factor of n in the recursive solution. So this function here compute the factorial of n. So this is how we can represent the factorial of n in the mathematical notation. So we have the function called fact here, and actually we just implement the formula we have here into C code. So first we just check out whether the current case is the base case. So we check out if the number of n equals to 0 here. If it is true, we just return 1. And if it is not true, we just perform this calculation here and then returns the value of these calculations. And you can see in this calculation, we have called the fact function again inside the fact function. But the only difference is that the argument here is not n, it's n minus 1. So let's check out what happens if we call this fact function. So let's assume that the function code is fact 3. So the initial number of n is 3. And in this case, the 3 is not equals to 0, right? So we will go to the else here. So the statement that will be executed is here, return. And in the current box here, the number of n is 3. So I write down 3 here. And the facts will be fact n minus 1. So 3 minus 1 is 2. So this is the first layer of recursion we have. That is 3 multiplied fact 2. Then we need to call the fact function again here because we have a fact 2 here. So when we call the fact 2 function again, then this function will be run again. So this is the second layer of recursion. So in the second layer of recursion, the current value of n is 2 because we have 2 here. So we just write down the 2 here. 2 is not equal to 0. So we run the return statements in the else here. So we have 2 multiplied fact 1 because 2 minus 1 is 1. Then we will call the fact function again. Then the 1 is not equals to 0. So we will run the statement inside the else again. So we just write down the 1 multiplied fact 0 here. So this is the third layer of recursion. Then finally we reach the base case because now in this case the number of the n is 0. So we just return 1. So we can immediately know the answer if we reach the base case. So we return from this layer here. So when we return 1, then we know this statement, the outcome will be 1 multiplied 1. So we just return 1 to the upper layer. So in the upper layer, we know the return value of fact 1 is 1. So we just calculate 2 multiplied 1, and then we return to the upper layer. So when we return to the first layer, we know the result, the return value of fact 2 is 2. So we just multiply 3 by 2, and then we just return to the function code of fact 3. So the output of fact 3 is 6. And this is a simple recursion example here, but if your recursion is more complicated, then sometimes you need to have a good technique to help you to trace the action of a recursive function. And actually, this technique is called box trace. And box trace is also how compiler usually implements recursions. And it can help you to debug recursive function. So let me quickly introduce how to use box trace strategy to understand the recursive function. So it's actually pretty similar with the figure I showed it here, just we have more systematic notations. So to use the box trace for the fact, this recursive function, the first thing we need to do is to label each recursive code in the recursive function body. Because in the more complex case, we might have multiple recursive code in the same recursive function. But let's start with a simple case here. So in the fact function, we only have one place, one recursive code. So we just label this recursive code as A, and we just keep track this place to which we return. It will return after the recursive code. So the recursive code is here, A, and then we just represent. We just use another way to visualize, to represent each code of the recursive functions, and we will use a new box to represent a new recursive code. And we also use the information in the box to remember the local environment of each recursion. So let's check out here. So here again we have the fact3. We use this function code, and then the fact3 will go to the first layer of recursion here. And in this layer of recursion, we know the current value of n is 3, right? And in the place where we have the recursive code, what we need to know is what is the output of fact n minus 1. And then we need to know what is the return value of this recursive function here. And then since we have called the function fact n minus 1 here, we just use it to draw another box here. And we add A here because the label of this recursive code is A. So it can help us to remember this is for the A recursive code. And then in the second box, we know 3 minus 1 is 2. So in the second box, in the second layer of recursion, the value of n is 2. And because we just repeat the same function in each recursion, so actually the label and the return is the same. We just continue to draw the function, to draw the box one by one. And you can see since we minus 1 from n in each recursion, so the number of n will decrease from 3 to 2 to 1 and to 0. And we know in this case, when n reach 0, that is the base case. And we know the answer immediately. So as long as we know the answer of base case, we start the return process. So we will return 1 into the previous layer of recursion. So in this case, we know the fact n minus 1 in this box will produce 1. So it will return 1 because 1 multiplied 1 is 1. Then we will just use this return value back to the prior layer of recursion. So you can see the recursion is like when this box returns the value, it will disappear. And after this box returns the value, the prior box can also return the value as well, because this is the smaller province compared to the prior layer of recursion. So we can start the return process until we reach the final layer of recursion. So that is how we can use the box trace to understand this fact recursive function. Okay, so let's try out another example here. So this example, I would say, is simpler than the factorial of n. So in this case, we want to compute x to the power of n. So we know that to compute x to the power of n, we can actually rewrite it into this formula here. We can rewrite x to the power of n into x multiplied x to the power of n minus 1. So we just follow the formula here to write down the following power function like this. So in this power function, the parameter is x and n, and we know the base case in the x to the power of n is where the number of n equals to 0, because x0 always equals to 1, no matter the number of x is, right? Like 2 to the power of 0 is 1, 100 to the power of 0 is also 1. So when the number of n is 0, we can know the answer immediately. And if n is not 0, we just round the statement here. So the statement just is identical with the formula here. And you can see here we call the power function inside the power function again. But in this time, the n we input for this function code is n minus 1. So using n minus 1 can let us make sure that the size of the problem will decrease as long as the recursion continues, so that we can make sure we can reach the base case eventually. Yeah, so this is the base case here. So what I want to invite you to do is to practice the box trace we just introduced in the previous slide by drawing the box trace by yourself. And the box trace you need to do is that let's assume that we have this code of power function 3 and 3. So I have drawn the initial box here for you, and I want you to do is to, if you have the slide right now, you can try to fill in the number we have here, and then try to draw the arrows by yourself to understand what is the relation between each box here. And if you have pen and paper or iPad on your hand, you can draw the box. I will recommend you to draw the box by yourself. So I will give you guys, because we don't have much time, I'll give you guys 1 minute to draw the box trace by yourself. So we will show you the answer when we reach 228. Or if you don't want to draw anything at all right now, you can imagine those boxes in your brain. Okay, so let's check out the result. So I hope you to get it right. So this is how your box trace should look like. So you can see we have every formula here, and then as long as we reach the base case, how the return value of base case should fill in the prior box. So this is the answer here, so you can try to compare these two figures by yourself. Okay, so here is another example of how we can shorten the power function by using a conditional expression in the return statements. So if you want to make your power function look fancier, you can try to rewrite the power function into this. So according to the two examples, the fact function and the power function, we can see that we always need to check if the current situation reached the base case or not. And if it is the base case, we need to return the correct value here. So all the recursive functions need to this kind of if statement to check if this is the base case or not. And if you forgot to add this kind of if statement, then you will probably have some infinite recursion. So infinite recursion means that your recursive function will not stop because it will never reach the base case. So the most important thing is to make sure your recursive function will reach the base case. So actually, that is the end of today's course. And that is all for you. That's all for today. I will see you next week.